Alright, we're going to turn a corner in today's video and we're going to stop calculating derivatives in the way that these examples have been calculated. We're going to start using derivative rules, which makes the process about 100 times faster. I hate to strip you of the glory that you felt when you completed one of these big long process derivatives, but I also am going to save you a bunch of time by teaching you derivative rules. And I've just kind of cut and pasted three derivative limit definition calculations onto this screen. I'm going to kind of divide them up. And you might have already started to develop this main rule in your head about how to take derivatives quickly. And this is just three more examples of a rule that we're going to simplify and speed up greatly called the power rule. This first derivative up here in red, the function was 2x squared minus 16x plus 35. The derivative was 4x minus 16. In blue we have 2x squared minus 5x plus 4. The derivative was 4x minus 5. And then down there in green you've got negative 1, or excuse me, just 1 over x. The negative was part of the formula. But 1 over x became negative 1 over x squared. So our goal is to figure out how you go from point A to point B in about 2 seconds rather than about 5 minutes. All right, we're going to take out all the limit definition and we're going to use derivative rules. Now the main derivative rule that will make up probably 90% of the derivatives you calculate is called the power rule. That's how we differentiate or find the derivative of a simple power expression where x is the base and the exponent is some number. Here's the rule, technically speaking. The derivative of x to the n is n times x to the n minus 1. And basically here's how you want to think of it. We're going to take the exponent. I'm going to write the answers to these 5 red examples in blue. Y prime, which is the derivative of y, in this case would be 3x squared. So basically what happens is the n, the exponent, drops down to the front and then it decreases by 1, turning into an n minus 1. So x to the 3, or 1x to the 3, becomes 3x to the 2. If there's a coefficient already sitting out there, which is why I added that 1 in, then you just multiply the power, the exponent that's coming down, by the number that's already sitting out there. So just from that very short explanation, see if you can predict what this next one's going to be. Okay, y is 4x to the third minus 3x squared plus 6x plus 5. Y prime is going to be 12x squared. All right, that happens when the 3 drops down to the front and multiplies by the 4 that's already sitting there, and then that 3 decreases to become a 2, resulting in 12x squared. Minus 6x, okay, so 3x squared becomes 6x, and if it was negative in the original function, then it's negative in the derivative. And then plus 6x, the derivative of that, is just plus 6. Now, interesting thing on the 5, maybe interesting, maybe just a fact you need to know, the 5 completely disappears from the derivative. The derivative of a constant like 5 is just 0. And I'll show you some of those on the next slide, but think of it. If you just had the function y equals 5, that would be a straight line graph at 1, 2, 3, 4, 5, and the graph has a slope of 0 everywhere we go, and since derivative is slope, this thing always has a value of 0. All right, so we'll talk some more about ones like those in a minute. Now, x to the 2/3, the derivative of x to the 2/3. This rule works whether n is an integer or whether it is a number like 2/3. The derivative of 2/3 is going to work exactly the same way. I forgot to name that one y, but let's say no prime there, just y. So y prime would be 2/3 times x to whatever 2/3 minus 1 is. And 2/3 minus 1 is negative 1/3. All right, it'd be 2/3 minus 3/3, so that's negative 1/3. And depending on the context, you might want to not have a negative exponent. We could write this as 2 over 3, and then that would be x to the 1/3 on the bottom, or I could even do the cube root of x on the bottom. You're going to have to deal with a lot. I mean, rules like, examples like my first two, Those are super fast. They're going to take you a few seconds each. Really, the only time power rules get tricky is just manipulating between different ways something can look. 2/3 x to the negative 1/3 is the same as 2 over 3 times the cube root of x. You just need to realize those things are the same and be ready for something to maybe not look like you anticipated it looking. All right, here's a similar one. 1 over the square root of x. Now, we've got two things happening. First of all, let me just rewrite y first before I even worry about the derivative. 1 over the square root of x. The square root is the same as a 1/2 power, and the fact that it's on the bottom makes it a negative 1/2 power. So these two things are identical. Now to take the derivative. The power rule doesn't matter whether the power is a whole number, whether it's a rational fraction type number, whether it's positive or negative. We're going to still apply the same rule. So the negative 1/2 drops down to the front in front of the x, and then I need to subtract 1 from negative 1/2. Negative 1/2 minus 1 is negative 3/2. And again, I could rewrite that one, and for the sake of time, I'm just going to leave that one the way it is. All right, so you're going to have to work with fractions a little bit, positives and negatives, and like I said, make sure you're ready for things to look in different ways, maybe not how you would first expect it to look. Now these are the type of functions you'll do as part of a bigger polynomial or just on their own. You'll be taking derivatives like this a lot. See if you can tell me, just pause and tell me these 4 answers, or tell yourself these 4 answers, and then resume and try them out. Okay, so 3x. This is 3x to the first, which you're not really going to think of it. We never really look at x and think x to the first unless we're trying to apply some rule like this. Long story short, and what you'll get used to doing, and it'll just become second nature, the derivative of 3x is 3. Okay, 3x is a straight line that goes through the origin with a slope of 3. And it's got a constant derivative. Straight lines have constant derivatives, which is why the derivative is a constant 3. Everywhere you go along that line, it has a slope of 3. Just like this next one, the derivative is 22. And we talked about that 5 on the end of the polynomial on the last slide. Same deal here. 6 and 2 pi are both just numbers, 0-degree functions. So horizontal lines like these two will always have a slope of 0. So the derivative of those values, of those functions, is 0, no matter what. Okay, so that takes care of the power rule. The power rule, like I said, is 90% of the derivatives you're going to take. And in this same section, we're going to deal with the 6 trig functions. We're going to learn how to take the derivative of the 6 trig functions. And I've got a picture to show you on the next slide, but for now, just make sure you have these 6 written down, and these are 6 that you just need to memorize. You will use the derivative of sine equals cosine a lot, cosine equals negative sine a lot. You will use tangent, the derivative of that is secant squared, a lot. The other 3 you will use sometimes, but you just never know when you're going to need it, so you need to memorize these 6 things. Starting now, you need to know them, and know them by heart without having to think much about it. Memorize them, make some flashcards. Now let's look at why the derivative of sine equals cosine makes sense. So I've got a picture here of sine and cosine graphed on the same axis. So a function's derivative is its slope at that x value. So for instance, let's look at cosine in blue and sine in red. And what we just saw on the last screen was that the derivative, if you want to say the derivative of something, you can say it like this: d over dx, and then in parentheses or brackets tell what you're taking the derivative of. What we saw is that the derivative of sine equals cosine. So no matter where I go, no matter how far left or right I go, the slope of the sine function should equal the value of the cosine function, or the height of the cosine function. So let's just start at the origin. Right here, this is, I've marked the sine going through the origin. Sine of 0 is 0. Right there, that is as steep as this line will get. After this point, it starts leveling back out to create that little hill that happens right over here. This is as steep as it gets. And right at that instant, the slope equals 1. Well, look what also is happening at that instant. The value of the cosine, it has a height of 1. So the slope of sine is the same as the height of cosine, and that's what it means to be a derivative. All right, and as you follow sine, as it moves along, sine becomes, at its max point, sine has a height of 1. But it has a slope of 0. The slope is 0, and look what has happened to cosine at that point. It has a height of 0. And I should use the word value. I mean, height is not really a technical term I want to use, but I think that just really illustrates what I mean. It's the value of a function is just the y value, which on a graph is how high that function is on the y-axis, on the y scale. Everywhere you go, no matter what, the slope of red is equal to the height of blue. We get over here to pi, just beyond 3. What's the slope there? That's as steep in the negative direction it gets. Here we go. Slope equals -1. Height, or value, equals -1. What I probably shouldn't do is exchange between height and value, but that's what I mean. Height and value, the same thing. It's the value of the function. Now, the other rule that we saw on there was the derivative of cosine is equal to negative sine. You'll probably spend a great amount of time trying to remember which one of them's negative and which one of them's not. The derivative of cosine is negative sine. So look at the slope of cosine. Right here at our first point, the slope of cosine is 0. The height of sine is 0. Right when we get to right here, the slope of cosine is -1. The value of sine is +1. So the slope's -1, the value is +1. All right, so that's why this negative sign comes into play. And that's going to hold true no matter where you go. These are both periodic functions. It's going to just keep repeating itself over and over. So take some time and look at a graph of these two things graphed on the same set of axes, and it'll just make sense. What's really important to be able to solve some problems is you memorize those 6, but here's just a little bit of hopefully deeper understanding. So what you need to know as of right now is how to use the power rule, even if it's got some funny powers like -2/3 or weird fractional exponents. And you need to know the 6 trig derivatives, and that will put you in good shape.